Hey guys, I'm Pamela. This is my presentation on the arbitrary Lagrangian-Eulerian methods and their applications in soil mechanics. So let's start off by defining soil mechanics. It's basically how physics is applied, or the theorems behind physics to soil. The first method we're going to introduce is the Lagrangian approach. In this approach, the mesh is connected to the material particles. So this is basically like how the speedometer in your car measures velocity. It's moving with your car, so the mesh is moving with the particles and measuring its deformation. So the material domain is a subset of the spatial dimensions, and then these are what the variables mean. So the mapping function is applied as a function of the material and time. This is the simplified formula. There are a few limitations that accompany the Lagrangian approach. Because the models are modeled continuously, they can terminate really quickly if large deformation happens. This can also lead to less accuracy. The Eulerian approach is next. So the mesh is fixed in this approach, and the material is analyzed with the fixed mesh as it moves. So this is like the experiment when you drop a ball in physics and you have these things that measure the velocity. The green things here are the laser devices which measure the velocity. They're fixed, but they measure the velocity at different times. The limitation that accompanies this method is that it's very reliant on the old information. Thus, this can cause reliability issues if you don't know what points you're using. You can lose accuracy depending on the points that you use, basically. This is why the ALE method was made. It combines both of the approaches in order to maximize the advantages and minimize limitations. So the spatial configuration or the material configurations aren't used. A third domain is used as reference instead of using either of those two. This is a picture which depicts the different functions and how the reference domain is used in the ALE approach. So in this section, I'm going to derive the basic formulas which are used for the ALE approach. So the material body is a subset of the spatial configuration, and its motion is defined with the mapping function, where the function is dependent on the points and the time. Material particles are obviously a part of the body. So this is where the arbitrary comes from. They use an arbitrary subset in order to define the reference domain. This only works, though, if the referential domain and the relative motion can be defined by the equation right there in yellow. The material velocity is defined by the equation right there, and the mesh velocity is defined by the equation with the W. So the difference between these velocities is called the convective velocity. Note that if we're looking at a Lagrangian approach, the convective velocity is equal to 0, and in the Eulerian approach, the convective velocity is equal to the material velocity. So mesh updating techniques are used heavily in the ALE approach. These can include mesh regularization and mesh adaptation. These are slightly different in their approaches, but they form the same function. They serve the same function. This is a picture that depicts the advantages to using the ALE method. And in my report, I analyzed a experiment which dealt with the penetration of strip footings into sand. And however, the ALE approach isn't always reliable. But it's definitely worth it to research it because it can be applied to different situations. These are the references which I used in white. Please feel free to reference them.